Hello everyone and welcome to the problem solving session of week 5. So I am Uditya from IIT Madras and will be hosting the problem solving session for this course on nanoBiophotonics touching our daily life. So this week encompassed of the fundamentals of flow cytometry. So to uh, to recall what it is, we will just go through overview and then we'll go to the problems. Yeah. So the word flow cytometry is basically it is a compound of two words. Yeah, flow and cytometry. So the term cytometry refers to the measurement of cells. Yeah. So that measurement can be either physical and or either is if only physical or chemical or both of cells, and basically and from cells cytometry you can go to other biological assemblies like proteins, DNAs. Yeah, so it starts with cytometry, but you can have multiple applications of it. And with the word flow, it's basically that measurements are usually made in a flowing condition. So the suspension of this biological suspension is made to flow in a single file past a sensing point. So how that sensing point and all are there, then that will be discussed. So that's the basic of flow cytometry. Yeah? Like how the word came. But then the flow cytometry usually have three main components. So it will have a flow system. So this is what will control the movement of cells past the sensing point. Then you have optical system, which is involved in detection. Yeah, you will have fluorophores. You can have the scattering properties of cells going past the sensing point. So, and you have electronic systems. In which the optical signals that you are acquiring, those are converted into electronic signals and analyzed by a computer and data, and you can like analyze the data. So you have these three systems or components present in a flow cytometry. So if we talk more on the flow system, one important aspect of this flow system is we get something called as a hydrodynamic focusing. This is an important part of a flow cytometry system, because the system is made such that the flowing sample is made in a single file, such that single cells, yeah, one cell at a time is going past the sensing point. So and this is done by some fluid mechanics. Yeah, basically they have a sheath fluid which goes so they will not have a like a boundary of fluid, like they will not have a pipe of a constricted length, but what they are doing is they are using the fluid as such that they are flowing non-turbulent fashion, like they won't mix also. Yeah, like for example in a flow system. Okay, so if the sample is coming this way and it will go like this will be the sheath fluid which will help. So this sheath fluid velocity will be higher than the sample. So what they will do is they will press it, yeah, compress this liquid, and but the thing is this won't mix with the sheath fluid also, it will remain as such. That's the magic of microfluidics. Yeah. And then you have on the optical system, what we have is the lasers, yeah, several lasers which are present, and yeah, then there are properties of that laser depending on its power, stability, and beam characteristics, noise, whatever is there. So, and also some of the optical responses that we get here is usually two scattered responses in terms of forward scatter and side scatter signals. Basically, forward scatter is something that gives idea of the size of the cell, and where the side scatter is something that gives the complexity or granularity of the cell. So, forward scatter, as the name suggests, is when the detector is placed directly, like in the path of the laser illumination. Whereas in side scatter, it is placed in not in the direction, or maybe in the perpendicular or some other direction, such that they can acquire the side signal that is scattered from the interiors or the granular structures of the cell. So the detector is usually placed at 90 degrees of the illuminating laser. Yeah. So, and plus then you have the fluorescence detectors. Yeah. And coming to these detectors, usually these detectors there are multiple detection systems. Some of them are photomultiplier tubes, which works on amplification of the electrical signal. Yeah. So the photomultiplier tubes or you have avalanche photodiodes. Yeah. Most of these are used because the signal that is occurred are in very low in magnitude, so you need some amplification to get it in a appreciable response. And in data analysis, you have several topics, like we have calibration. Yeah. So in most of these fluorescence cytometry, they use calibration using polystyrene beads or those latex microbeads. So those are something that are so these microbeads are used. So because the dimensions of these microbeads are comparable to the cells, which are comparable to biological cells. Yeah. And then you have some concepts on compensation, compensation gating. So compensation is something that if you have multiple fluorophores, you have to take care that the signal from one fluorophore does not spill over to the other fluorophore, because there can be some overlapping in their signals. So that checking that out is compensation. And then you have gating, in which you can have grouping of your data. Yeah. So grouping of your populations of the data. So that's what. So it can help you. So it depends on your experimental design, and it can give very much good correlations which you can derive from your experiments. Lastly, we discussed something on applications, where you would have seen its application in a lot of areas, like immunophenotyping. Yeah. Then on the detection of the cluster domains. Yeah. Cluster of differentiations in different cells, basically the immune cells, CD markers. Yeah. Then cell cycle detection also we can do using this. So a lot of applications there. and it is an great tool. People use it extensively in immunology. Yeah. Then something we learned about Raman assisted flow cytometry. So a brief on Raman spectroscopy, which is a non-destructive technique, and it's a scattering technique. So basically, it works on when you incident a light and then the light gets scattered. Usually, that light, some photons, like 1 in 10 to the power 6 photons, undergo a Raman spectroscopy. So it is quite a low number of photons undergoing it. So some of these photons will have lower energy or higher energy. So depending on it, that change in that energy is basically because of the vibrational modes of that molecule. So you can basically use that to characterize the entities in the sample. And then if you do this Raman on a rough metal, like rough metal surface like gold or silver, then you get something called as surface enhanced Raman spectroscopy. And it essentially boosts the signal that can be occurred with only Raman spectroscopy. Yeah, it's kind of a boosting or enhancement. So there are some Raman spectral flow cytometry, so which those are very good in providing molecular specificity, and because these are Raman, which every compound kind of have a which are Raman active usually have a molecular signature peak. Those will give a signature spectroscopic graph it will give. So you can have multiple like multiplexing. You will have a lot of multiplexing abilities because you can go on acquiring the spectra of those things. So it will expand it expands the area or the number of samples, number of characterizations or measurements we can do. Yeah. So a great tool for deeper understanding of cellular and molecular processes, and you can expand it to metabolic, to molecular composition, chemical structure. Yeah, so a good technique. So we'll go to the problems then. Which of the following is a common method used to achieve hydrodynamic focusing in flow cytometry? So the answer is laminar flow. So laminar flow helps in aligning cells or particles in a single file uh, within the center of the fluidic channel. Yeah. The flow cell of a flow cytometer is usually equipped with So the answer is all of the above. In modern flow cytometers, different types of spectrometer, different types of detectors may be employed depending on the specific application and instrument configuration. So you will find both like photomultiplier tubes and avalanche photodiodes are quite used, and you will also find charge coupled devices also currently in some of the instruments. What is the purpose of the sheath fluid in a flow cytometer flow cell? So the answer is to focus the cells into a single file stream. So as the sheath fluid flows faster than the sample stream, confines the cells to the center of the flow cell, ensuring that they pass through the laser beam one at a time, allowing accurate and precise analysis. So basically getting data from one cell at a time. Yeah, that's what is the focus. So what is the purpose of sorting gates in a cell sorter? Uh, so yeah, then the option has gone off. A, to align cells into a single file stream to control direction of cell flow, to identify cells of interest based on specific parameters to ensure laminar flow of sheath fluid. So the answer is to identify cells of interest based on specific parameters. So by setting specific sorting criteria, the gates allow the sorter to selectively divert cells meeting those criteria to separate collection tubes for further analysis or downstream applications. The following cell types is expected to have a higher SSC value in flow cytometry. The answer is lymphocyte. So basically, site scatter is related to granularity or internal complexity. Yeah? So lymphocytes usually have more granular in nature. Unlike monocyte, yeah, basically the monocytes red blood cells, which are non-nucleated. So yeah, lymphocytes will have higher site scatter population. Here the following is an example of a commonly used fluorochrome. So the answer is rhodamine. Rhodamine is commonly used fluorochrome in various biological and imaging applications due to its high quantum yield, brightness and photostability. Its excitation and emission wavelengths are visible spectrum, making it compatible with standard fluorescence imaging systems. How does an avalanche photodiode amplify signals? So the answer is by using a high gain internal amplifier. So by using a high gain internal amplifier, an avalanche photodiode amplifies weak electrical signals generated by incident photons. This internal amplification is achieved through the avalanche effect, where the initial photogenerated electron triggers a chain reaction of electron multiplication, resulting in significantly higher signal output compared to conventional photodiodes. Which of the following is a challenge of Raman assisted flow cytometry? So the answer is lower signal intensity compared to fluorescence detection. The Raman scattering signals is weak in comparison to the strong fluorescence signals typically obtained in conventional flow cytometry. Raman scattering is an inherently low intensity phenomena which can limit the sensitivity and detection capabilities of Raman based techniques. So therefore we go ahead with surface enhanced Raman, to enhancing the signal. When gating in flow cytometry, what does the term positive refers to? So cells that exhibit a specific marker or fluorescence signal above a defined threshold is considered to be the positive, in gating. So that's all for today. And any questions there? You can ask any questions. Otherwise, you are free to leave the meet. So we'll meet again next week, same time. So yeah, thank you.